In 11.2, we're going to talk about arcs and chords. Now, let's first start off with two vocab words. A central angle is an angle whose vertex is the center of a circle. An arc is an unbroken part of the circle consisting of 2 points called the endpoints and all of the points on the circle between them. So let's go over a picture here. This angle here, angle ACB, that would be the central angle. Now there are two types of arcs, which we'll talk about in a little bit. But an arc is an unbroken part of the circle, such as arc AB. That would be the minor arc. The major arc would be arc ADB or BDA. But there's one thing to make note of. When you're going through here, and when you are naming minor and major arcs, this is important. Minor arcs may be named by 2 points. Major arcs and semicircles must be named by 3. So let's talk more about arcs and their measures. A minor arc is an arc whose points are on the interior of the central angle. The measure of a minor arc is equal to the measure of its central angle. That's important. The arc and the central angle are exactly the same. And here's how you'd write it. The measure of arc AC is equal to the measure of angle ABC, which in this case is x degrees. A major arc is an arc whose points are on the exterior of the central angle. So if you look right here, the central angle faces this way. The major arc is the points on the exterior of that. The measure of this arc, now this should make sense, if the central angle is the same angle as the minor arc, you know all the way around would be 360, then you take 360 minus the minor arc, or minus the angle measure, which are the same thing, to get the major arc. If the endpoints of an arc are on the diameter, then the arc is a semicircle. And you should know that, for example, the measure of angle EFG would be half of a circle. So that would be 180 degrees. So in example 1, the circle graph shows the types of music sold during 1 week at a music store. Find the measure of arc BC. Arc BC, if you look right here, is rap. Well, the measure of arc BC is equal to the measure of angle BMC. Well, 13%, we would take 13% of 360 degrees, which would give us 46 8/10 degrees. So the measure of arc BC is 46.8 degrees. Adjacent arcs are arcs of the same circle that intersect at exactly 1 point. So for example, arc RS and arc ST intersect at point S, so therefore they are adjacent. Now, the arc addition postulate. The arc addition postulate is just like the angle and segment addition postulates we've done in the past. The measure of an arc formed by 2 adjacent arcs is the sum of the measure of the 2 arcs. So if I added together arc AB and arc BC, that would give me the measure of arc ABC. So in example 2, find the measure of arc CDE. Well, CDE is right here. We know that's 18 degrees. Well, I'm going to draw this bigger here. Well, since we know this central angle is 90 degrees, this arc is 90 degrees. Because of vertical angles, this is 18, which makes this 18 degrees, which makes the arc 18 degrees. So I would add together 90 and 18, so the measure of arc CDE would equal 108 degrees by the arc addition postulate. Within a circle or congruent circles, congruent arcs are two arcs that have the same measure. For example here, if we have two central angles that are congruent, then their arcs are congruent. So arcs ST and UV are congruent. Which leads us into three very, very important theorems. In this first theorem, now these are all the same theorem in this book, but it doesn't matter what the theorem number is. This is in a circle or congruent circles. If central angles, now remember, the hypothesis are what you know, the conclusion is what you state. So, congruent central angles have congruent chords. That's what you'd say. If the central angles are congruent, then the chords are congruent. Angles are congruent, the chords are congruent. Congruent chords have congruent arcs. So, congruent chords have congruent arcs. And then congruent arcs have congruent central angles. So basically, if we have central angles that are congruent, we know their chords and their arcs are also congruent. We're actually going to prove this theorem. So in our given, angle BAC is congruent to angle DAE. So we know the central angles are congruent. We want to prove that chords BC and DE are congruent. Well, there's our given. We know that AB is congruent to AD and AC is congruent to AC because all radii are equal. Well, instantly, what do we have here? We have these two segments congruent, and we have these two segments congruent, which means we have two congruent triangles by side angle side, and therefore we can say that the chords BC and DE, those segments, are congruent because of CPCTC. Example 3. Find each measure. Segment RS and segment TU are congruent. Find the measure of arc RS. Well, if we know that remember once again, if we know the chords are congruent, then we know the arcs are congruent. So let's say that again. If chords are congruent, arcs are congruent. And so what you would say is, as a reasoning, if chords are congruent, arcs are congruent. So we would say 3x equals 2x plus 27. That gives us x equals 27. We plug it in, and 27 times 3 will give us the measure of arc RS, which is 81 degrees. In B, these two circles are congruent. Find their arcs, or find the measure of angle DEF, which is this angle here, if their arcs are congruent. Well, if the arcs are congruent, the central angles are congruent. So 5y plus 5 equals 7y minus 43. That gives us 2y equals 48, which gives us y equals 24. Well, if the measure of angle DEF is 7y minus 45, we plug that in. 7 multiplied by 24, subtracted by 43, gives me the measure of angle DEF as 125 degrees. We have 4 more theorems to go over. Theorem 12, 2, 3, and 4 say this. If I have a chord and a radii that are perpendicular, so if a radii or a diameter are perpendicular to a chord, then it bisects the chord and its arc. That's important. That means CD, segment CD, bisects both the segment EF and arc EF. If in a circle, the perpendicular bisector of a chord is a radius, or you could say it's a diameter. So here's what we're given. If we know JK or AK is a perpendicular bisector of the chord GH, that means, now once again, we were given 90 degrees and it's bisected, then we could say either segment AK or segment JK would be the diameter or the radius, depending on which one it is. Now this Chords theorem has not been given to you, so we're putting it in here. It says this, that in the same circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. So, if AB and CD are congruent, they're only congruent if and only if EF and EG are equal, the distances of them are. And you'll notice they form right angles. So example number 4. Find the length of BD. Here's B, here's D, and here's EA. Now, normally, I wouldn't even give you that dotted line there. We know this is 2, we know this is 3. I want to find BD. So what do? Well, we know AD is 5 because this and this are both the radii of the circle. So this is 3. So the length of CD here has to be 4 because it's Pythagorean theorem. It's a 3, 4, 5 Pythagorean triple, which means this is also congruent. And if I asked you, you had to tell me the reason why, you would tell me that you knew that since you know this is perpendicular, you know this is bisected, so they're both 4. So the length of BD would be 8. And your vocabulary for this section are these 7 words.